So there are very few research studies, very, very few, that I have read and immediately thought the results were so powerful they needed to be blasted from the rooftops and everybody should know about them. But here's one. Two British professors, Eddie Gray and David Tall, worked with 72 students between the ages of 7 and 13, and they had asked teachers to nominate students they thought of as above average, average, and below average. They then gave the students various addition and subtraction problems to do, and they categorised their strategies. For example, they gave them problems such as 7 plus 18, which is the addition of a single-digit number to a teen-digit number, as you can see here. And what they found was that students used 4 different strategies when they worked on number problems. So the strategies were, some students counted all. So with 7 plus 18, they would say 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, and count up to 18. And then to add them, they would count them all again, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and go on like that. The slightly more sophisticated strategy of counting on is when students would add up to 7 or to 18 and then continue on. So if they'd added 18, they would then say 19, 20, 21. Known facts was when students just knew what the number bonds, they just remembered them. And what they called derived facts, which I would call number sense, and which this whole session is about, was when students were able to break numbers apart and decompose and add them and use them flexibly. So for example, they might say with 8 plus 17, I'm going to take 8 plus 2 and make that into 10. Or they may break 17 into 15 plus 2 and then calculate 15 and 2 and 8. So they make the problems into easier addition problems. And the results from the 8-year-olds was stunning to me. So the above average students, 30% of them knew the numbers, they used facts, known facts. 61% of them used number sense, so they used the numbers flexibly. And 9% of them counted on. In the below average group, 6% of them used known facts, none of them used number sense. 72% of them counted on, and 22% counted all. And when they worked with the 10-year-olds, they found that the below average group were using the same number of known facts as the above average 8-year-olds. So they're sort of caught up on the number they remember over time. But still virtually no number sense, and instead they were continuing to count. So why is this finding so important? The researchers who did this study put it well. They concluded that the low achievers, so often thought of as slow learners, were actually not working more slowly, but they were learning a different form of mathematics. And what's more, the mathematics that the low achievers were learning was the more difficult form of mathematics. So let's think about this issue of the more difficult mathematics with the case of counting back. Counting back is a strategy that young children use when subtracting 2 numbers. So when you consider a problem such as 16 take away 13, if you start at 16 and count down 13 numbers, 16, 15, 14, 13, 12, you'll find that this is actually an extremely difficult task, and it has significant cognitive complexity and enormous room for error. By contrast, the strategy of the high achievers, let's subtract 10 from 10 and 3 from 6, which leaves 3, is much easier to use. And those are the type of strategies that high achieving students are able to use. So the fact that high achievers had learned to act upon numbers flexibly and the low achieving students hadn't is important, really important, because the flexible use of numbers and shapes is critical to higher level maths learning. In fact, it's foundational for everything that comes above, all the higher level work in algebra, calculus, and beyond. So the problem for low achieving children is not that they cannot work in these ways, but they haven't learned to engage with maths in those ways. And the researchers found that when the low achievers failed using their counting methods, they didn't change their method, but they fell back into counting more and more. And the problem for those students comes about because they may become efficient with repeated counting of small numbers, and that lulls them into a sense of security, and they come to believe that maths is about counting very precisely. Unfortunately, as time goes on, the low achieving students only have these counting strategies, And the counting gets ever more complex as problems become more difficult. And low achievers also are often identified as low achieving in school, and the help that they then often get is more procedures, more emphasis on doing procedures very carefully rather than being taught to use numbers flexibly, and that's probably the very, very last thing that they need. So part of the seriousness of the problem is this. Mathematics is a conceptual subject. It's not just a series of procedures and methods, although many people think it is. For example, if we think of the hierarchy of concepts in early number, we know that students start by learning to count, and that helps them to develop the concept of sum. Then they work on counting on, and that helps them to get the concept of addition. And when they work with repeated addition, that helps them develop the concept of a product. So when we learn mathematics, we engage in a process in our brain that's called compression. And this is how it works. When we learn new material, it takes up a big space in our brain. So if I was to teach you some new mathematics now, you would be thinking about how it works, where it fits, how it fits with other methods. So it takes up a very large space. But if you were to use some early mathematics now, such as addition, you would probably just very quickly be able to recall and use that. That addition is not taking up a big space in your brain, it's compressed. And this is William Thurston. He was is a Fields Medal winner in mathematics. And this is him talking about compression. He says, mathematics is amazingly compressible. You may struggle a long time, step by step, to work through the same process or idea from several approaches. But once you really understand it and have the mental perspective to see it as a whole, there's often a tremendous mental compression. You can file it away, recall it quickly and completely when you need it, and use it as just one step in some other mental process. And the insight that goes with this compression is one of the real joys of mathematics. But here's the problem. Students who don't engage in conceptual thinking don't benefit from compression. So we can represent compression, the compression that goes on in the brain, as a kind of triangle in this way, with the space that's taken up with new mathematics at the top of the triangle. But for students who don't see mathematics conceptually, for them it's less of a triangle and more like a never-ending ladder that stretches up to the sky, with method upon method upon method. So they're not thinking of mathematics conceptually. Instead, they're thinking there are lots and lots of different methods to remember. And so they're not engaging in this process of compression. So in mathematics education and policy documents, people have for a long time talked about procedural methods and conceptual ideas, that maths is made up of these two kind of areas, with a big divide between the two. So people talk about it's either conceptual or it's procedural. But Carolyn Kieran's done some really interesting work, which has shown that actually we need to use mathematics conceptually even when we're just learning procedures, because every time you need to use a procedure, every time you need to adapt a procedure, you engage in conceptual thinking. So those distinctions between the two are probably not even that helpful. So we have what people think of now as an algebra crisis in the US. Everybody's worried that large numbers of students are failing algebra and that maybe algebra is just too difficult or too hard. But one of the main reasons students fail in algebra is a lack of foundational mathematics, particularly number sense. So it's very difficult for students to learn algebra if they've missed out on a foundational understanding of early number, and they've missed out on developing number sense. So one of the people I interviewed for this course, a very interesting person, is Sebastian Thrun. He's achieved many things. He's a Stanford professor, a vice president of Google, and he was the one who designed the self-driving car and Google Glass and other things, and he's now the CEO of Udacity. And I interviewed him about his use of mathematics, and I'm going to show you more of the interview in the next session. But when he reflects on his work and talks about various things he's done. But one of the interesting parts was he talked about how everything he's done in his work, including writing complex mathematics papers and using a lot of high-level mathematics, comes down to an understanding of numbers. He talks about addition in particular and how everything else falls into place. So this is a short extract that I'd like you to watch and listen to now.
I think everyone exercises math every day in the way we operate. We think about time every day, we think about money, we think about relationships of people, how they interact with each other, we think about tasks, about things we have to do, about deadlines. These are all mathematical examples, and if you step a step further, there's more contrived example like financing of your house and so on. They're a little bit more difficult to manipulate, but even there we can get an intuition of what's going on, and they're mathematical. I actually believe that almost everything in math is addition. Almost everything can be derived back to very, very simple operations, like putting numbers together is the core of all the mathematics. I'm saying this, I've written a fairly abstract math book full of formulas and formulas and formulas. You would, like, your head would smoke seeing all the formulas. And still everything in there is just basically addition. So I think the key thing is not to be afraid of the formulas. The formulas are just a language. The key thing is to grasp the concepts and understand where they apply. The key thing is to understand that certain rules apply regardless of the context. For example, adding apples is the same as adding pears. And once this abstraction is done between an instantiation of a concept that might involve time or space or people to another instantiation, you already have the basic math skill, which is the idea to abstract, the idea that there's rules that transcend beyond a certain domain. And simple rules are very powerful. Complicated rules are not very powerful in my opinion. They are simple rules. So rules that say we can add numbers and we can keep track of them, or there's some sort of constancy to certain things, like the way space evolves and so on, are really powerful.
So what I'd like you to do now is think a bit about what we've seen so far and what you've heard, and answer this question.